All right, welcome everybody. It is my pleasure to host our next panel on direct air capture, CO2 transportation, and geologic storage. My name is Simon Peng. I was one of the Roads to Removal authors leading the direct air capture chapter. I lead our direct air capture program at Lawrence Livermore National Laboratory. We do a lot of work kind of in the technology development, the chemistry, engineering space, and also think about kind of, as we'll see in a moment, kind of where we can put direct air capture at large scales around the country and what are the resources that we need. We've obviously heard a lot earlier today on some of the opportunities in Wyoming, and I think we're just going to continue to hit that point. There are a lot of opportunities here to implement direct air capture at really large scales. I just want to echo Representative Larson's remarks earlier that Wyoming really has incredible resources here, energy resources, pore space resources, and I think we'll see a lot of that through our discussion today. So let's see, is this on? There we go. All right, so we're talking about direct air capture and storage. So in this case, we are talking about technologies that can grab onto CO2 from the atmosphere at the relatively low concentration that it is, and then produce a concentrated carbon dioxide stream, somewhere in the maybe 99.5% purity realm, such that you can then use it for converting into other chemicals or storing underground geologically. Kind of traditionally in the discussion of direct air capture, there are two main classes of direct air capture technologies that people will talk about. And I'm not going to get into a lot of the details of the chemistry or the engineering for these different ones. I'm happy to offline, where maybe I won't bore most of the audience. But we have one strategy that is based on using liquids that will react with carbon dioxide in the atmosphere. You can pump these liquids around into different processes, very similar to how you might move fluids around a chemicals manufacturing or oil facility or refinery, and eventually through a series of processes, you're able to produce a high purity stream of carbon dioxide and then reuse that liquid to recapture more carbon dioxide. The other kind of major form of direct air capture is using solids to capture the carbon dioxide, and it works very similarly in that the solids now, instead of the liquid, react with the carbon dioxide in the atmosphere. And then again, through a series of processes, you create that high purity stream of carbon dioxide and you regenerate that solid so that you can use it again to capture more carbon dioxide. That kind of reusability of the materials in this case is really important to avoid generating a lot of waste associated with a single pass, one-time use of these things. Common to both of these types of processes is the need in that regeneration, in that production of the high purity stream of CO2, the need to apply significant amounts of energy, frankly. And often in these two examples, you're applying that energy in the form of heat. And it can be heat at different temperatures. A lot of the solid processes will use something like, around steam temperatures of heat, about 100 degrees Celsius. Whereas that other process, the liquid process, uses temperatures up to 800, 900 degrees Celsius, depending on the exact process that you're using. And so that quality of the heat really matters, and so where you get the energy for that heat will also matter. All right, so JP showed earlier in her slides kind of our end results for where we ended up for direct air capture and kind of the potential across the United States. And really what jumped out at us when we were doing this analysis is that Wyoming looks really good for direct air capture. I've shown here kind of the blow up on the right there of the counties of Wyoming, really next door in Carbon County, and then further over in Sweetwater County, really big opportunities there, and then up in the northeast in Campbell County as well. I do want to highlight kind of the small box there that says the DAX capacity. We're talking here something on the order of tens to hundreds of millions of tons of carbon dioxide per year that these counties could support, in principle, if you wanted to build out all of the direct air capture capacity in these counties. That's a really significant amount of carbon dioxide that you can move, enough to supply carbon dioxide removal or carbon dioxide streams for other industries for the country. Maybe not all of our carbon dioxide removal needs, but a very significant portion of it. Okay, so why? Why is there such a huge opportunity in Wyoming? What leads to this? So for direct air capture, and particularly direct air capture with geologic storage, you basically need two major things. You need energy that I already mentioned. You need that energy to produce the high purity stream of CO2, and you need somewhere to put that CO2, the geologic space. We'll hear in just a bit more about kind of why Wyoming geology is really good for storing carbon dioxide. You've seen this map already. The green spaces are where there's really, relatively inexpensive CO2 storage that we know, there are large kind of volumes of CO2 that you can store. So I'm not going to belabor this too much, and Scott will give an excellent kind of tutorial on this as well. In terms of energy, obviously Wyoming, huge energy state. We've talked about, or we've heard about this. It's going to be an all of the above solution in terms of energy moving forward. Wyoming obviously has a lot of abundant traditional energy sources, as well as future energy resources. There's a lot of wind energy, obviously, as many of you know, in the state, and this wind energy can go to powering things like direct air capture. And so while, large-scale deployment of wind energy or wind farms may not generate jobs in themselves, the facilities that they go to power can. And so, we really looked at this and, this map, sorry, I should explain what this map is showing. We're looking at, in green, kind of the solar generation potential, and in blue, the wind generation potential. And this is on land where we don't have to change what the land is doing. So we're not building over, we're not putting a lot of solar panels over like forests and things like that, right? We're not going to stick a wind farm in the middle of the forest. We have slope considerations. So, that's why you see in the northwest of the state where you have a lot more, rock, the steeper mountains, you're not going to necessarily be generating a lot of additional electricity there. And so, Wyoming really is kind of blessed with some of these future energy resources as well as all of the traditional energy resources. All right, last point that I want to make is, and I think there was a question earlier about kind of the suitability of direct air capture technologies for Wyoming's climate. There are a lot of different direct air capture technologies. There's the liquid, there are solids, but even within liquids and solids, there are a lot of subclasses of different technologies that use different temperatures for regeneration. They use different kinds of chemistries, different engineering to be able to capture that CO2. And so I think one huge opportunity is really to design technologies, design chemistries, design processes that are suited for individual climates. And so, like I mentioned earlier, what might work really well in Texas or in the Gulf Coast might not be the solution for direct air capture in Wyoming. I think Mindy introduced herself earlier, but Mindy's from Spiritus, and they have a Class 6 well permit in Wyoming. They're planning their first kind of pilot facility up here. And so excited to see what comes from that. But yeah, like I mentioned, a bunch of different technologies, a bunch of different opportunities. So with that, I'm going to hand it over to Scott, who will give a couple of remarks as well.
All right. Should I just use the podium mic? Okay. I'm going to move over so my shadow is not in the picture. So the geologic storage chapter in the Roads to Removal report is written by a dear friend and colleague of mine, Susan Herborka. I think many of you probably know Sue if you're in the carbon capture world. Sue is a really great communicator, and she likes to break things down to the very basics. So I'm going to stand up here and channel my inner Sue, and we're going to break it down to the very basics of carbon storage. And I'm hoping that if you haven't been introduced to geologic storage before, you leave with a little bit more understanding. I see a lot of faces in the room that have a very high understanding of carbon storage, so maybe your takeaway is this is how I can help communicate it to others in the communities that we're working in. Okay, so what is CCUS? We've been talking about it all day. It's really the capture, the transport, the utilization, and the storage. And in Wyoming, just like we have an all-of-the-above energy approach, it's kind of an all-of-the-above carbon approach. So that capture facility on this, most of our conversations in Wyoming, we're talking about point source capture. So we're talking about capture on a coal-fired power plant or a natural gas-fired power plant. So a coal-fired power plant has about 13% CO2 in its flue gas. So that capture is really just separating the CO2 out of the rest of the stream. If you go to natural gas, that's more about 7% CO2 that comes out of that flue gas. Now, if you go direct air capture, you're at like 0.04% CO2, right? So you're very, very dilute streams. Cement, you can get all the way up to like 30% CO2. In Wyoming, we have a large enhanced oil recovery industry. So it takes about 2 tons of CO2 to produce a barrel of oil. How much CO2 is in a barrel of oil? About a half a ton. So through enhanced oil recovery, we can actually get a lower CO2 barrel of oil. Now, what we're talking about today is geologic sequestration. If we're not using that CO2 for enhanced oil recovery, we can take it and we can put it into a Class 6 well, which we'll hear more about it from Lily, and we can store it deep underground. So Randall talked a lot about this, so I won't belabor it. But why is CCUS good in Wyoming? Or so we have lots of large emission sources. We've got coal-fired power plants, but we also have a large mining and manufacturing sector in the trona industry. It's the largest, in Sweetwater County, that's the largest trona production in the US. It's our second most important mining industry. Customers care about carbon. When they're looking at something they want to buy, it doesn't matter if it's energy or if it doesn't matter if it's a product. We have to be able to tell them that we're able to manage that carbon. So does everybody know what trona is? It's a huge component of glass. So if you drank beer out of a glass beer bottle in the US, 100% of those are made out of Wyoming trona. So it's not just about energy, it's also about our mining and manufacturing industries here in Wyoming. So Wyoming has the right geology, we keep hearing that. So what does that mean? So this schematic here, we've been working with Basin Electric at Dry Fork Power Station to do a commercial scale feasibility geologic storage project at that facility. We've drilled 2 wells, we've shot 3D seismic, we've done geophysical well logs, we've done all the science we need to do in those wells to really understand what it takes to store CO2. So across Wyoming, very deep, at this location we're 9,000 feet, so almost 2 miles below the subsurface. We get lots of stacked geologic intervals that can store CO2. And so what does that mean? What's the right thing, or what's the right geology for CO2 storage? First, you have to have the space. You have to have a container that's big enough to put the CO2 into. And if you put the CO2 into that container, into the subsurface, you have to have some sort of cap or cap rock to hold it in there. And just because you can physically put it into the ground, you also have to have that friendly legal framework that allows you to do it. And so in Wyoming, as has been mentioned several times today, that legal framework has been developed that allows us to put CO2 into the subsurface, use our fantastic geology, and hold it there for geologic timescales. So Wyoming rocks. Here's some rocks from Wyoming. So that rock on the left, you're looking at about a 4-inch section of rock. So this would be a geologic core. We would drill a well, you bring the core of rock up, it's about 3 inches wide there. So if you zoom into it, if you take a slice of it and zoom into it under a microscope, you start to see those little grains pop out. If you zoom in even further, you can see those little minerals in the rock. Now that blue space, that's pore space. That's what we're looking for to store CO2 into. So that is a micrograph on the right, zoomed in. We take blue epoxy and dye it so that pore space jumps out at you. That's what the landowners in Wyoming own. That's what they can lease and rent to CO2 project developers. And that's where we will put CO2. The other concept about CO2 is how much is a ton? We always talk about a ton of CO2. So if we were here in this room right now and we had a ton of CO2 in front of us, you can look at that balloon there. That's about how much space a ton of CO2 takes up. It's about 1.5 cows. I don't know what happened to the other half a cow. It's probably in Jenny Gordon's Beef to Backpacks program. But CO2 is an interesting substance. If we heat it up and we compress it, you get a huge volume reduction. That's why we want to put it in the subsurface, because we have pressure down there that can take CO2 and store it in a huge volume reduction space. And so we call this dense phase CO2. It's also called supercritical. So it behaves like a fluid. It has properties of water, but when it flows, it kind of flows like a gas. So that's why we're so interested in using that pore space below. We can take this huge volume problem of CO2 on the subsurface, make it small, and keep it under the subsurface. Okay, so here's a little geologic model built from that micrograph picture that you've seen. So basically, we've got a little cube of pore space here, and we're going to put our CO2 molecules into it. So think of it as like a container. And when you get it into that container, then you have to put the lid on it. When you keep the lid on it, it's going to stay there for those geologic timescales. So what does this actually look like in the rock? So on the top picture there, that's a mudstone. So that's what we call a cap rock. These are at the same scale underneath the microscope. So that mudstone, you can see it doesn't have that porosity and it doesn't have that permeability. That rock is sitting on top of the reservoir that we put the CO2 into, and it holds it in there. That's our reservoir rock on the bottom there. So utilizing that pore space, you get that shale or mudstone on top, and it keeps it in the container. Okay, so just last parting thoughts. I want to talk about the commercial projects that are ongoing in Wyoming. So I mentioned Dry Fork Station. That's with Basin Electric up in northeast Wyoming. They emit about 2.2 million tons per year. We've been working with them since 2017 to design that project and let them understand what a commercial project would look like. We're getting to the point now where we're almost through our NEPA phase, and we'll be applying for a phase 4 project to take this to a full commercial build out. We're just starting with Frontier Carbon in the southwest part of the state. So that's a Sweetwater Carbon Storage Hub. Those were the first 3 Class 6 wells approved in Wyoming. We'll be drilling those probably starting early next year. I saw Eric here earlier. I don't know if he's still around. But Southwest Wyoming is a really exciting place for geologic storage. We've got the best reservoirs. We've got a lot of emission sources. We've got really high potential in that area. We're working with Williams at Echo Springs, a gas processing facility, to look at what storage could look like in the Wamsutter area. And then Tallgrass, a commercial developer, is developing the Eastern Wyoming Sequestration Hub that's bringing CO2 from the Midwest into Wyoming for storage. Okay, I will end there.
Great. Thanks, Scott. And I apologize, I should have introduced Scott at first. Scott Colin's the Senior Director of Research at the School of Natural Resources right here at the university. Next up, we've got Matt Fry, who is the Policy and Technology Director for Carbon Management at the Great Plains Institute, and I believe either recently or in the very near future will also be affiliated with the university.
Can y'all hear me? Great. So afternoon, how is everybody? That's correct. I'm Matt. I'm currently with GPI, and then in a couple weeks, I'll be working with Scott at SCR. So I'm going to do this slide because I'm basically obligated to do it in every presentation on what GPI is. We're a small nonprofit. We're not technologically affiliated with anything. We're nonpartisan. Basically, what I work on is policies that help support the deployment of projects that maintain affordable, reliable, and clean energy across the country. So now to dig in a little bit, wanted to talk a little bit about where we are in the U.S. with project deployment, proposed project deployment, just with the incentives that there are in place and the understanding of the technology as to where it is now. So as you can see, this data is probably not up to date because it's hard to keep up with it at this point, but these are the projects that are proposed across the country right now, or announced across the country right now. You can see they're at various stages and status, but what you can also picture is that not many of them are operational right now. There's a lot of reasons for that. We can talk about it later, but just think about this. This is a currently evolving technology and evolving market, so things are coming online as technically and financially feasible. What you'll also see here is these proposed projects would amount to about 200 million metric tons of annual captured CO2 from point source, and potentially 7.5 million tons with DAC. As we talked about earlier, we need to start talking about gigatons, which is billions of tons, but we're making a good head start if we start putting these projects on the ground. Next thing I'll mention is where we are from a dollars perspective. So this is potential investment across the country in carbon management projects. This is full scale, like this is capture, this is transport, this is storage. It also includes hydrogen, hubs, DAC, all of the things that are ongoing at this phase. Rough math, that's just over about $6 billion in proposed investment. I see this misrepresented a lot because people say this is investment in carbon management. It's not. We haven't gotten to the actual spending of dollars now. We're in the pre-spending of dollars. So this is what it could look like if these projects were deployed. So what's this mean for Wyoming? At GPI, we too like data. We like to crunch numbers. Some of my colleagues in the room, Carbon Solutions, we work with them on data crunching as well as other folks. So a few years back, it's probably going on 7 years back at this point, we did an analysis that looked at what the potential best case scenario, build out scenario would look like for carbon management in the mid-continent region. Wyoming was obviously in that mid-continent region. So these, based on what that deployment scenario looked like, we also partnered with the Rhodium Group, who's very well known for their analyses and their analytical capabilities at what you can generate from a revenue and a jobs perspective. So we partnered with them to use that deployment data as to what the job and economic opportunities were. This information is all available at our website, but just bringing out the high points here. Based on our analysis, there's potential for $11.2 billion in private investment in Wyoming of carbon management. This is specifically capture, transport, and storage. We have a later analysis that looked at DAC, but this is specific to capture, transport, and storage. 2,650 project jobs, so that's development jobs, build-out jobs, early jobs. Just under 2,000 operational jobs, like those are the permanent jobs that are associated with operating these projects in the long term. And then the 690 infrastructure jobs, those are related to pipeline infrastructure, the build out and the development of those infrastructure. So what we can't do is analyze how this compares with job loss as the energy industry transitions as to whatever that may look like. We all have our own opinions. They're just opinions, and we'll figure that out, but we couldn't quantify what that job loss was going to be, so we didn't pretend to analyze it. And I'll transition a little bit with just that thinking as to where we are in Wyoming, what the potential is, and kind of follow up with what Randall talked about earlier today. Wyoming, for literally nearly 20 years in both the legislative and the executive branch, has been a leader in policy and statute that helps support a carbon management industry. We've honestly done it because we need to protect our interests and our financial opportunities. We did it early. We looked at opportunities and ways to support the enhanced recovery operations across the state. As we mentioned, we talked about statutory, foundational statutory things such as pore space ownership. Additionally, in 2012, the legislature provided a $2 million budget to look at opportunities to build out pipeline corridors across the state, with the understanding being that we could use these pipeline corridors through an environmental analysis with the understanding that we are 50% federal land and we have to build linear infrastructure across federal land, that we could give folks a head start. We could, by doing this analysis, we could reduce their time and cost and their permitting process. So what we did was, with that legislative funding, we built out a corridor system across the state that looks at sources and sinks, both geologic storage and enhanced recovery. It's a 2,000-mile pipeline corridor, but the authorization is specifically to federal lands. I manage this project for the state. It took literally about 12 years to do it. It took 10 years to get the BLM to say they'd do it, and it took 2 years to actually do it. So, so with that, we are literally the only state in the country that has a corridor system in place. And for that, we're pretty lucky because it could minimize or reduce future permitting obligations as we build out these infrastructure. And just for folks that don't know, we have just over 5,000 miles of CO2 pipelines in the country now, depending on which analysis you read. We need somewhere between 30 and 90,000 miles of CO2 pipeline to meet our objectives. And I won't talk much about Class 6 because Lily's here, but I just wanted to provide this slide to let folks know that along with all of our statutory framework and the pipeline corridors and everything, Wyoming was very was very wise in seeking Class 6 primacy because it takes forever to get a permit through the EPA. Lily does it a lot faster. She does it probably better. And so we were ahead of our time, I'll say, as being the second state to achieve primacy. So that's just saying that Wyoming's well positioned to continue our leadership in carbon management, and all of the things that we've done will help facilitate our continued ability to develop our fossils and other energy resources. That's all I have.
Great, thanks, Matt. All right, and then last we've got Micah Christensen, the Natural Resource Counsel for the Wyoming County Commissioners Association.
Good afternoon, everybody. I am not a professor at SER, so I'm not going to put up a slideshow for you. Well, let's talk a little bit about why in the world I'm up here. Since I'm not a scientist, I've spent very little time with carbon capture technologies and understand very little of it. Thank you so much for informing me. Now I have something to talk about. But a little background on myself. Graduate from the University of Wyoming College of Law and clerked for Chief Judge Skavdal and Casper. Then moved to the Oil and Gas Conservation Commission and served as their Attorney General. Also represented the Enhanced Oil Recovery Commission while I worked there before transitioning to the Wyoming County Commissioners Association. My job is unique to, I think, the nation, and that is it is funded through a state appropriation through the Federal Natural Resource Policy account. The governor then gives money to the association to hire a natural resource attorney to assist local governments in their relationships and really putting them on the map for working with federal agencies on land management planning. There's a saying amongst the commissioners that if you're not at the table, you're likely on the menu. And so we spent a lot of time in Wyoming working with our federal partners to make sure that land management policies and plans make sense, and taking a more comprehensive look at how even what might seem like slight changes or variations, and if you've been around in this space for a while, colossal changes in natural resource management and direction, how it can affect not only local economies, customs, and culture, but also opportunities like DAC, like continuing to export, as Randall Luthi mentioned earlier, 12 times the energy that Wyoming consumes. And so really, I'm, I guess, on the panel to talk about more of a holistic approach and look at some of the pieces of carbon management and what it might look like even at the local level, which does help with some siting and does play a big role in how we work with our federal partners managing roughly 50% of the surface estate and 2/3 of the mineral estate in Wyoming. I think maybe I'll just spend a little bit of time talking about following up on what Randall and Representative Larson talked about with Wyoming and not only our historic industries. We have a really small degree of separation in Wyoming. We know a lot of folks. You don't want to say anything bad about folks in Wyoming because it's likely, you know, someone's neighbor or cousin or school teacher. And so, but similarly, we have a very close degree of connection to a lot of our natural resource industries. I'm a Wyomingite. I forget how many generations now, but I have miners, coal miners from the northeast in my family. They mined coal up in Monarch. I also have miners in Hot Springs County, quarries. And I think a lot of folks in Wyoming have connections to those industries, which is a great advantage to the state. We've talked about how great the rock is, we've talked about how great our natural resources are, but one of the things that we like to focus on is the value we have in our people. Our people here have a high energy IQ. They understand not only the processes, but also the needs for clean, renewable, reliable, all those pieces. And I think that that plays really well to our advantage as a state, because a lot of these things, whether it be getting oil and gas to the ground or putting CO2 back in it, can be understood by sort of our general populace. We have a social license to operate in this space. We have large, as you saw on the map, we have large mines, we have large industry. I mean, the oil and gas industry in our state pays a substantial portion of local and state taxes. It's one of the reasons why we don't have a state income tax. I see the state treasurer here. It's really important to our state to maintain these industries. And the nice thing about Wyoming is, as you just heard, we're already doing a lot of these things. So like I said, I served as the counsel for the Enhanced Oil Recovery Commission, focusing really on getting more oil out of the ground, more gas out of the ground, utilizing secondary, tertiary recovery, pipelines, infrastructure, all those things, working with industry partners to capitalize on the things in Wyoming. But again, we sort of understand that we also have, I believe Chute Creek is still the world's largest carbon capture facility. So we're already doing it, and we've been doing it for decades. Even before some of the conversation around, I think, DAC and other technologies have been around, we've been implementing some of these pieces. And so I think we have a lot of opportunities as a state, but with that great opportunity comes a great responsibility to be thoughtful about how we not only manage our carbon, but also how we treat energy. And taking a comprehensive look at all of the resources that we care about in the state. I asked earlier a question about this page, I think it's on 19, about where this might look. Is this federal land, is this private land, is it state lands? And it matters because if it's on federal lands, you have more than just wilderness areas to deal with. You've got trails and view sheds and ACECs and PHMA for sage-grouse habitat, and WSAs, and you have migration corridors, and you have view sheds that you have to be protected. There's a whole host of resources that have to be brought into the equation, and that's why it's so important that we have not only state and federal partners involved, but also local partners, county commissioners, very to the earth where the rubber hits the road, so that we can make sure that when we cite projects and we have that need for community buy-in, we have support of all the players, because it's going to take certainly more than just one industry, one business, one partner. It's going to take all hands on deck across the state. So that's my opening. I didn't even talk about DAC. Did you see that? No. Thanks, Simon.
Fantastic. Yeah, and as you can see, we have a really diverse set of experiences and spanning policy, technology in above ground, underground. So I have a number of prepared questions, but kind of given the time, I actually want to turn it over to audience questions to make sure that we have enough time for everybody. So yeah, one over there.
So this is just a two-part question. This is definitely not my area of expertise. So the carbon capturing that you just presented is not removing CO2 that we put in the atmosphere over the last 100 years, but it's allowing us to continue producing fossil fuels and removing it at that source. Is that correct?
So we've talked about, I think, a couple of different sources for carbon dioxide. Some are looking at point sources where you may be, say, burning a fuel and capturing the carbon dioxide off of that. That's, say, the coal power plants or the natural gas power plants. Some are off of chemicals facilities, so like the Trona facilities that were mentioned. And then we're also talking about things like direct air capture, removing the CO2 that's already in the atmosphere.
Okay. And then the second question is, you mentioned that it sounds like some of the capture is going to be at the source and then pumped into the ground near the source, but some of that CO2 is going to be transported. Have you done like a full life cycle analysis to figure out the offset of how much CO2 is and energy that's being used to transport the CO2 that we then can stick in the ground? And are we actually leading to like a net removal of CO2? Just curious.
Yeah, so that's the goal, right? To get to net zero or carbon removal. So you're right, you have to do a full wells to wheels approach. You have to understand the full life cycle analysis. I think that's where enhanced oil recovery comes in. I think that's going to be interesting to look at. Can you maximize CO2 storage but still produce oil or an energy mineral? The Roadster Removal Report didn't look at point source capture. It fully looked at direct air capture and its potential to be deployed in Wyoming.
Yeah, I would just add that life cycle analyses are very challenging because people argue about where you start and where you stop. There's a lot of analyses out there that look at the life cycle and whether it's a net benefit. I think some of those are very emotionally charged. So when you read those, just make sure that you understand where that starting point is and where that ending point is, and you're getting the information that you really want when you read them.
I guess I just have to be on every panel. I apologize. But I had a question. You know, when we've encountered direct air capture, the two questions that came up the most is how much water is going to be used and how much power is going to be used. And there's a big NIMBY issue that comes along with that. Are there ways to help with the NIMBY issue and to help with the how much water is going to be used? Because I've never had a direct answer about how much water is anticipated for these projects.
I think maybe one of the reasons you're not getting a direct answer about how much water is going to be used is because it will depend. I think with a lot of things in direct air capture, because it's not a single technology, there are a class of different technologies, because it depends on the environment that you're deploying in, it'll depend on the water use. So in say a colder and drier climate like Wyoming, yeah, you might actually have more water use for some technologies. So the liquid solvent technologies, where you're contacting a lot of water with the air. Yeah, you're going to lose a lot of water. For some of the solid technologies, maybe less so the case. In terms of energy use, it's large. There's no getting around that fact right now. There are a lot of people, a lot of academics, a lot of companies looking into how to reduce that energy use, just because it's a major cost for them as well, right? It's in their interest to reduce that. But yeah, today's direct air capture technologies, are not necessarily the ones that are going to be deployed at the megaton scale, the 100 megaton scale, in their current form.
Okay. I guess a follow-up on the energy thing. You've got nice little diagrams there as far as the processes and stuff, but it would be nice to say this is either so many kilowatts per ton or so many BTUs per ton at this stage and this stage at this stage, and then at the end you use X amount of energy, whatever basis you want to per ton or per million tons or whatever. So you kind of understand, actually the energy formula that moves through there. But I got maybe that, I hope, a question that would be a practical question. Under the southwest Wyoming, there is a huge pool of lithium, and it's at very, very low concentrations. And I'm just wondering if there's any capstones over that, because I'm thinking that it isn't possible right now to economically, pump that stuff to the surface because of the low concentrations. But if you could pressurize that whole reservoir to where, and I think it would just be a huge amount of carbon dioxide to pressurize it and bring that up to where it was economically viable. So, and it might take 50 years to pressurize a reservoir or something, but it seems like looking at it not as a tertiary recovery, but a primary recovery of a mineral resource. But I don't know the geology, but I didn't know if anybody could speak toward the geology over that, if there's any capstone there to where you could actually make that functional.
Yeah, so I can talk to that. So the lithium that you're talking about is dissolved in brines, so it's dissolved in a salt water, particularly in the Rock Springs uplift, so in southwest Wyoming. Those brines that we found, and I was one of the folks that measured them, were found in the Madison Formation, and so about 10,000 feet below the surface at that location. The Madison is a great reservoir for CO2 storage. And so when we looked at the lithium brines, they're a concentration of about 100 parts per million, or 100 milligrams per liter. So kind of sub-economic on if it's just a lithium business. But how we looked at it is, okay, we need that reservoir for CO2 storage. If we produce the brine out of formation first, it allows more room for CO2 in that formation. So in order to make that an economic project, it's now being looked at as a CO2 storage project that you put CO2 in, you produce the brine out to make more room for the CO2, and when that brine's at the surface, then it has to be managed, and then you can treat it and harvest the lithium. 10 years ago when we first looked at it, marginally economic. Now the technologies are coming up where the cost of treating that water and harvesting the lithium, it starts to look like it might pencil. So it is an interesting project. I'd love to do a little more work on it.
Would it take 50 years to pressurize that?
The reservoirs of the Rock Springs uplift can take all of Wyoming's CO2 every year for over 500 years. That's how much storage space is there. And so it could be a really large regional CO2 storage hub.
We've got time for one more question.
Hi, I'm a postdoc at the UW. So just a past study have found that the CO2 storage can cause earthquakes. So you mentioned that we are building a large scale carbon removal projects, including like CCS or DEX or BECCS. So how do you think that it may have the negative energy environmental impacts?
Sorry, I didn't quite hear the question at the end there.
So past study have showed that CO2 storage in the saline reservoirs may cause earthquakes. So I was concerning that the large amount of CO2 stored may cause negative environmental impact.
I feel like I'm hogging the mic.
It's all yours.
So there is risk in a CO2 storage project, right? You have to understand what the pressure is. You have to understand what the groundwater quality is that you're putting CO2 in. You have to really understand your rocks. The Class 6 permit that's required before you can put CO2 in the subsurface is really, really robust and rigorous. They go through all those different scenarios of what the risk is to the project and what environmental concerns are there. And so the Class 6 permit, if you get through that, then you've pretty much de-risked your project. Did that answer your question?
All right, let's thank our panel.